Welcome. All right, what do you got? Bring it on. Yeah.
Third sentence.
Third sentence. Boy, I'm going to have to pull up the exam, aren't I?
Right. So, one, when it says rescale the total integrated amplitude, so first we normalize them separately, and then we're going to go and combine them and rescale?
Yeah. Yeah, so what you're going to do is take your, it's just like the unit vector from the last time. You'll take your spectrum and then make sure that if it sums to 1, so 1 over the summation of all the elements in the spectrum, you'll divide the spectrum by that. And so therefore, if it's normalized, right? That's your normalized spectrum, and then you'll multiply that by 20.
So do we normalize them separate?
Yeah, each one you'll normalize independently.
Okay.
So that every one of them will have the same amplitude, and it'll be easy to recombine them. And then we'll treat this just like a simulation with low signal to noise, where we have a read noise. So there's a random Gaussian distributed random variable with a mean of 1, and that adds to every pixel. And then there's also a Poisson distributed number of counts on top of that.
So,
go ahead.
yeah.
If there's follow-up questions, let's take care of those first, though. Is this a follow-up to this one?
Yeah.
Okay, good.
When we calculate the Poisson, it's based with every one of the means in each point?
Yeah, that's exactly right. So in other words, if I choose this particular pixel, and I have, after normalization, I have a mean of the Poisson equals 0.02. Then chances are you're either going to have a 0 or a 1 there, and very low probability of having something higher. But that is exactly what you'll say for that pixel. Do I have a 0 or a 1? Or some other higher? You'll pull a single number. Well, honestly, the easiest way to do this is all wavelengths at a time. Right? So if this is, I'm using my hands again. I forget that I have to do it on here. So if we think of this as being wavelength down or wave number, these are Raman spectra, and trial in this direction, then in terms of programming, it's actually easiest to make, 260, what do we say? 200. It's easiest to make 255 random variables with the same Poisson mean.
But is 1,000?
I don't, this is what I'm asking, see?
Yeah.
Okay. See, who led me wrong there? Yes, this axis is 255, this axis is it 1,000?
Yeah.
Okay. So it's easiest for each wavelength to make 1,000 variables in terms of programming, because that way, otherwise you have to have, otherwise you're making that Poisson call all the time for every place you go, every one of the spectrum.
After that, you have to add noise.
Yeah. Yeah. And I think someone else asked the question, if once you normalize, you end up with negative values, and if you try to calculate the Poisson of a negative value, MathCAD says, hey, you're trying to do something I'm not allowed to do. In that case, just put 0 in.
Still
Sorry?
want to do it with 0.
Oh, okay. They just don't evaluate a Poisson variable at all for that. In other words, don't ask it to calculate a Poisson with a mean of 0. Just don't do a Poisson at all unless the number is higher than 0. So if you put in an if statement before the evaluation of the Poisson,
can we offset the spectra instead? Because I already did that.
I haven't run it that way, so I don't know what havoc it might wreak. To be honest, we're really talking about collectively.
And normalized.
Yeah, what we're really discussing by saying that is what's our how much do we care about how we treat zero? So it shouldn't really, at the end of the day, matter one way or the other. It's not as clean of a simulation that way. Let me leave it at that, though. As long as these are all questions related to the same question, I say we forge on. You had yours up, and then we'll do that one.
So once we have all of our Poisson distributed numbers, so I'm getting numbers from like 0 to 4 depending on the mean that we had. And then to that, we're just taking whatever noise we randomly generated and just the number that we got from the Poisson plus the noise.
Yeah. And the noise will have a mean of 0, so sometimes it'll add positively, sometimes it'll add negatively.
Yep.
But there is a problem with that. The noise is too big for the normalized, and the spectrum is just lost.
Well, if you have the mean of your, as long as you multiply by 20 prior to doing that,
Yeah, even in that case.
even still it's that big?
Yeah.
Well, let's see, what do your spectra look like?
I have a question.
Did it, when I plotted my spectra, they looked kind of like this.
The normalized one?
Rescale. Yeah. So you take the spectrum, normalize it. It looks just like the regular spectrum, just smaller. Run the Poisson and add noise, and it looks kind of like that.
Okay.
So, how are we generating the mean for each of these Poisson calls? So, do we need to basically take the mean for a specific pixel?
Yeah, so for example, if we go back to here, if we look at this particular wavelength,
Yes.
it's got, after rescaling, it has some amplitude.
Yes.
That amplitude is the mean of the Poisson.
Okay, so we are not factoring in the other spectra whenever we're doing the Poisson calls. It's just
Well,
the
you're,
spectrum.
You're actually, it's going to be that times 20,
Yeah.
right? That will be the mean of the Poisson.
Yes.
In other- So you normalize, multiply by 20, use that value for the mean of the Poisson as long as it's greater than 0,
Okay.
and then add noise.
To the Poisson.
After
After you've calculated the amplitude of the Poisson, then you add noise to that.
So then in your...
So, just to clarify, and then I'll answer this question. In a real experiment, this would be equivalent to having two sources of noise. One is the fundamental Poisson uncertainty in the terms of the number of photons at that particular wavelength, and the other is read noise. The read noise is constant, irrespective of how many photons are there. That's the normally distributed value. And the Poisson noise has to do with the number of photons at each wavelength. So in terms of mimicking an experiment or simulating an experiment, that's why we chose this. I hope that helps. Maybe it didn't. Okay, your question.
So then for the 3D LDA program, we have like the A0, 1, those matrices. It has the rows, columns across and the rows down. Yeah,
Columns.
columns.
Yeah.
Yeah. So going across would be our 1,000 in the LDA program, and down is for each wavelength. So it should be like a...
Yeah,
1,000
I believe it should be structured in this way.
Okay.
Wavelength on each column is a spectrum,
Okay.
and the column number corresponds to a particular spectrum.
Sure.
Yeah.
So you want, just to clarify, for the noise, that standard deviation of 1 would be an equivalent amount of noise to plus or minus 1 photon on the
If you,
detector?
well, yeah. So on a CCD camera, you have no gain, so that'd be equivalent to 1 electron. Yeah.
There is a difference between the spectrum. The gain starts in a different value than the other.
Oh, in terms of the horizontal axis?
Yeah, just one.
Oh, it's
shift.
shifted by 1 pixel.
Yeah, the wavelength is different in that one.
I'm open to whatever creative solution you have for that one.
Can we just, when we're doing that calculation, with that in mind, if I can piggyback on top
choose one of those rows and stick with it instead of having to tweak our program?
Yeah, that's fine.
back and forth?
Yeah, I'm not going to care if the simulation will not care, and the final outcome in terms of what you learn from the course will be impacted by if the spectrum is shifted over by a 4 wave numbers. So whatever practical solution you have to forget about that and still sleep well at night, I'm okay with. I hope that made sense.
Yes.
Okay. All right. More questions? Yeah.
Is it
Oh, well, okay.
possible that there's a typo in question 1?
No, it's impossible. Outrageous.
Is SW, I have the same for both, and SB is different.
Where is this?
So it says that
This is
you
for
get
A?
two different
1A?
results for the SW matrix in part A, and I got 2 different results for SB and the same for SW. I don't know if I just did something wrong, or I thought it was.
Oh, no. Yes, you're right. It is. It's SB
Okay.
and not SW. Wow, okay. Yeah. Make a note of that. We're going to have to make a correction. Actually, let's do that right now. There! So that's SB. Here too? Yeah. It's weird. It's irritating that it does that, but if you look up algorithms for doing LDA, then this is a standard algorithm. The multi-class system you would think would be better improved because it has a weighting for the number of elements in each class, and it is improved, except it gives the wrong eigenvalues. So if you actually want to use the eigenvalues, you need to rescale them back. Yes.
For B, in B we have to create also 1000 spectrum.
Yeah.
So we have to calculate the misclassification graphically and using analytical expression or something,
Sorry, ask the question again, please.
because we have like 2
So-
questions in B.
Oh, B. Okay.
Yeah.
This is my heat waves coming up here. All right. The question is in B. It goes back to what we did on the first exam in terms of
And
probability of
then we have to
misclassification.
do it again with a different approach.
Yeah, because it's a different Z expression. It's a different expression for Z because now it's going to be in terms of J.
So
For
we
example.
have 2
Yeah.
different. Okay. So one according to the last exam, and a new one using this approach.
Yeah. Now, it won't be that different, but it'll just be a slightly different analytical expression relating the probability for misclassification to the corresponding eigenvalue J.
So J is the eigenvalue.
Yeah, J is the eigenvalue. I'm repeating back what you're asking because everybody who's listening to my computer won't know what you just asked. I don't know if anyone's listening to my computer. Probably the FBI. They're probably trying to hack into this right after my iPhone. Yeah.
In part A, when you say 2 of the different algorithms, 2 class and C class, what are we doing in terms of the generic C class? Because I thought we defined that C.
Could you ask your question one more time? So this has to do with 2 class versus C class.
Right.
And it turns out that there was a simplified expression for calculating for optimizing and determining the eigenvector W in the 2 class system than in the more general C class system.
Okay, so I got you now.
So, both of them generate exactly the same eigenvector because the eigenvector is normalized. But and they do it by optimizing and identifying the eigenvalues. It's just they end up with 2 different rescaled forms of the eigenvalue.
So related to that, on the website we have a LDA example 1D and 3D.
Mm-hmm.
So is this referring to when it says 2D in the question, does that mean the 1D online?
Yes. Okay. Yes. Yeah, that should be 1D. I should change it because it's a 2-class 1D. It's not 2D.
Okay.
That's a very good point. Yes.
In the C, we have to change just 20 for 100.
Yeah. You'll increase the number of counts to 100.
So, but before generating the 100 spectrums.
This is the mean counts per spectrum. So this is what you're doing to rescale that.
So we need to rescale it first before generating the 100.
Well, there'll be two separate. The easiest way to do it is to just write two programs, or write two regions in the programs. One with a mean of 20 from part A, and then this one where it's increased to 100, because you're now discriminating between 4 classes instead of 2 classes. It makes sense that you'll need better signal to noise, and that feeds in nicely to the rest of the calculations in part D and E. Yes?
So in the part A, we just choose 2 different wavelengths, and for the part C, how many wavelengths should we choose?
Part A, you should choose 256 wavelengths.
All of them?
Yeah.
Why does it say to select 2?
Where does it say that again? Right here. Pick the 2 wavelength. Okay, so the idea. This is actually following the example in the MathCAD file.
Yes.
And the idea is that we want to get a sense for how well things are improved if we include all 256 wavelengths, as opposed to just selecting the 2 we think might offer some discrimination. Imagine you were doing this with the Spec 20. Who knows what a Spec 20 is? Yeah, a lot of people, especially if you taught. Most of you haven't, but we had them in our Gen Chem labs until just recently. So Spec 20 is an absorbance measurement at 1 wavelength. And then you turn it over to another wavelength, and if you wanted to discriminate between 2 species, you choose 2 wavelengths that had very different absorbances, ideally. Ideally, there'd be no overlap. But in the case that there are, you just want to maximize the differential absorbance between each of those 2 samples. So if you look at the Raman spectra, and find 2 wavelengths where one has a peak in one and is nice and baseline in the other, and the other one is the other way around, those are probably going to be representative wavelengths that should provide some reasonably good degree of discrimination. So you can do that by, and the template is already in the MathCAD file, so there's not much you have to change except selection of the appropriate wavelength. Just find a peak in one and find a peak in the other, and then you plot in the template the 2D, and you should see some separation between those if you choose wavelengths that are appropriate. It will improve if you use all 256 and reduce dimensionality down to 1 as well. But this is the equivalent of what this is well, it's actually a 2-dimensional problem. It's 2 wavelengths, but it's actually higher dimensionality than LDA would do. But it's just to illustrate the improvement upon going to multi-wavelengths and doing the full LDA as opposed to just selecting 2 wavelengths.
So then what you would do then is you'd select 1 wavelength for one compound, one for the other, that gives like the maximum peaks, and then for both of those wavelengths, for each spectra, you would take the data from each compound at both of those.
Yeah.
So you would just be, so it would be like 1,000 by 2.
Yeah, so what you'll end up with, I'll show it here, I'll illustrate it here. So, if I have 2 spectra, let's say I choose these as the 2 wavelengths for doing this initial first pass at the ability to discriminate, right? This is no LDA, this is just dumb taking 2 wavelengths and seeing if we can separate the 2 spectra based on just those 2 individual values. And I have a bunch of these, right? I've made 1,000 of those, and I've made 1,000 of these. And if I just look at the red ones, they're going to have a high value for lambda 1 and a low value for lambda 2, right? So they're going to be sort of scattered around here. Each one of them, there's randomness associated with it, so I'll have 1,000 data points, all centered around lambda 1 higher and lambda 2 lower, right? And then the blue one will sort of be more like this. And they may, oh, come on back here. They may be sufficiently broad that there's significant overlap. I don't actually know. I have to see what wavelengths you choose and how it plots. But that's the idea. There's some discriminatory capability just from looking at those individual wavelengths. Yeah.
So this became a little unclear for the course of that answering. You want us to do both?
Yeah.
Both just two wavelengths and all 255.
Yes. And the reason I don't feel bad requesting that of you is that that example is exactly already provided in the template. So the only thing you really have to do is massage the input data and apply the appropriate, just tweak the numbers in there. But there's already an example of selecting two wavelengths and making these scatter plots in the template for LDA.
Now, should we do both for both the 1D and the 3D?
No, just for the 1D case. By that, after you've done it for the 1D case, you'll have moved on to brighter pastures. Yes.
So when we correct, it tells us to determine the difference between the two algorithms and then correct it. Will that produce the same SB matrix for both of them then, if you do it correctly?
So the question is, if we do the correction appropriately, do we end up with the same SB matrix as well as the same eigenvalue? And the answer is a resounding yes.
Okay.
So we need to perform the 1D with the normalize and then scale spectra too?
Yes. Yes. The question is, do we do the 1D after this whole rescaling, normalization, and adding of noise? Yes, that happens. That's why it's in Part A. You'll do that for everything that you'll run. Because you need to have some mimic for noisy data. And what you're given as your inputs are not. Yeah.
Should the plots look terrible?
Yeah.
Okay.
Yeah, right. And one easy thing to do to make sure things are working is jack up that mean from 20 to 1,000 and just make sure that they start to look okay again. But the idea, of course, for this is to have crappy spectra that still have some ability to resolve things based on fishing signal out of what looks like noise. So yeah, they should be pretty noisy. You should look at them and think, ah. Or worse than that.
For F in that question, we have the unknown spectrum, but we have just the signal, so we need to assume that the wavelength is the same.
So this is, yes. Assume that the wavelengths are the same, because so the question is, this whole question of the appropriate scaling of the x-axis, the horizontal axis in terms of wave number, assume that these are all in the same units as the training data.
Because in the unknown, you just have one.
That's correct. In the unknown, it's just a column of data. There is no x-axis, there's just the y. Assume that the x-axes are similar.
So again, we have to deal with the difference between the initial wavelength.
No, again, you have to ignore the difference between the initial. Yeah.
For 1D, it says, the last part of the question says, show by substitution that the Z statistic can be evaluated by such and such.
Yeah.
Is this done on Method or is this handwritten?
Handwritten.
So that is just to prove that. Huh?
Yeah. Yep. It's pencil and paper component to convince yourself that this is not crazy.
D is pencil and paper as well, right?
I can't touch that screen. Better touch this one. You said B? Yeah. Yeah. It's relating. That's analytical. An analytical derivation relating delta to J. Yeah, even in the age of computers, every once in a while you got to sit down and do stuff by hand and figure it all out.
But for B, the first part, we did it using MATLAB in the last exam. So one part MATLAB and the other one.
I'm trying to think what you would do in MathCAD to derive an expression.
No. For the probability.
I'm sorry.
B.
B?
What is a probability suite?
Yeah, what is it? That means specification. We did it using MATLAB in the.
Oh, well, you can use that expression to determine the probability for misclassification. You'll do that using the numbers from here in terms of the mean, in terms of the eigenvalues. Based on the eigenvalue and based on the numbers that you get from part A, you should be able to determine the probability of misclassification. So you have you'll derive an analytical expression, and that's the pencil and paper part. And then using the values from A, you'll have to turn on MathCAD in order to actually generate the probability for misclassification, to put it into a real number. So it's not entirely pencil and paper. You're correct. Well, let's make sure we're all done with question 1, but definitely we have time for question 2 as well. Any other questions on number 1?
I just have a quick clarification question.
Sure.
Going back to something we were talking about earlier, once we generate the Poisson data, and you said that before we add the noise to the Poisson, we have to calculate the amplitude of the Poisson?
Yeah. Do you want me to go through that process a little more clearly? Because that's a potentially confusing part, and it's the start. So you've got a spectrum. You'll normalize, normalize. Normalize so it sums to 1. We'll call this spec. And we'll call this spec n, just for example. That way I'm not in the glaring glow of my white screen. Boy, that was a mistake. I should have gone with white on black instead of black on white. Okay, anyway. Normalize it so it sums to 1, and so therefore the sum over I of spec ni equals 1. Let's see, so you'll multiply by 20, and then use each you'll for each wavelength wave number. So for each wave number, you'll use whatever value you got once you rescale the multiply by 20 as the mean of the Poisson, and you'll generate 1,000 Poisson distributed numbers with that mean. Then repeat. Well, we can do it. In terms of order of operation, I don't know what's easier. But we'll go ahead and add in. No, I don't want to end show. Add in the normally distributed 1,000. Add to a vector of 1,000 normally distributed numbers. Yeah. And then And then repeat that process for every row in a matrix. Is that clear?
Yeah, that's clear. So basically, you could also create a matrix for the normally distributed that's going to be like 1,000 by 255.
And then add that after the fact as well. Lots of different ways of doing it. Why is it? I'm brushing against it somehow? I'm not sure what's going on here.
And then that final matrix is what you put into the template?
Yeah.
Oh,
Yep.
okay.
That feeds directly into the LDA algorithm.
All right. Thank you.
Yeah.
So that, the LDA has the matrix with the brackets around it. What I'm getting is a table. So it's columns 0 to 1,000, or 0 to 99, 0 to 254. Is there a way to go from that to a matrix?
They are, I believe, mathematically equivalent in MathCAD. It's just how it's displayed.
Okay.
If it gets too big, then it will put scroll bars on the left and right,
Okay.
because otherwise it can't display all of 1,000 times 256 values.
Okay.
So it looks like a table, but it's still mathematically a matrix. Most likely. Never can tell with MathCAD.
That's true.
Any more questions on number 1? No? Okay. On to question 2.
We have to plot using the number of students or the probability?
Use the actual number, like the number of students.
You'll want to remember to repeat the question. So
Yeah, the question is when you plot the data for question part A, question 2 part A, are you using the probability or the actual numbers? I would say just actual numbers, like the number of students.
Should we do a weighted or unweighted linear model?
Unweighted.
Unweighted.
Yes.
Are we calculating chi-square for part A?
Nope.
No, right?
Oh,
Because it mentions
Yeah.
in one, I think B or C, compare the chi-square.
sure.
with
You
that.
yeah. Then
So
just
you are-
calculate. Yeah, it's just like residual sum of residual squares. It's the same.
So that's my question, because for the C part, we
Mhm.
have to fit a function, but with probability.
Yeah.
Yeah.
But when you actually plot the data, like you can convert the probability back to the number of students. Yes.
You said that there was an error with this one.
Error with.
There was like a problem with the question.
Yeah, there is a problem with linear fit. So
What's the next step on that?
so just like determine why the linear model may fail sometimes, and state why we need like the generalized linear model for part B and part C. Yeah.
For part C,
Mhm.
when we're using the template, I guess I'm kind of having a hard time understanding what equation is the input. Like, because we know that it's binomially distributed, and we know that it's also following this exponential.
Mhm.
And then we're giving these linear predictors and link functions, and I'm not really sure how all of that.
Yeah, it's actually just the link function itself. Link function G whatever equal to the linear predictor. So in the, for example, logic model, if I remember it correctly, it's log P over 1 minus P.
Yeah.
It's equal to beta 0 plus beta 1 x.
So for in the template, the original equation is like an f of x
Mhm.
equation,
Mhm.
and I guess
Yeah, there's a way to
there's
do.
a way to convert that into the form that it needs to be for the template.
You can do it. The easy way to do it is actually transform your fx. So transform your data into this form.
Okay.
Any other questions? Yes.
In 1b, are you taking n is equal to 1 in the binomial function?
N is equal to, you can keep n in the equations. So don't use a specific number for n.
So you predict in 1 way, right? So n is equal to 1.
What do you mean by? No, n is not equal to 1 in our case.
To
You want to maybe put
clarify-
the question up?
Oh, sure. How to do that?
Easiest one is this one. And then it's here. Okay.
Where's the?
Just a clarification
Mhm.
about near the end of part B, d prime of theta is the first derivative with respect to theta of z of theta.
Yeah. And likewise, the second derivative. Yes.
Just to make sure, can you define MLE that is in part A? Would you like to tell me what that acronym means?
Sorry, it's maximum likelihood estimation.
Okay. Just make, yeah.
Is the maximum likelihood estimator equivalent to the least squares?
Yes, in the linear model, like simple linear model, yes.
Okay. And
So just do the matrix inversion, and you can figure out the answer, like the alpha and beta matrix. So,
Yeah.
Yeah. Any other questions?
I have a question, but it wasn't related to really anything, any of the questions. The points don't seem to add up.
Really? Okay, I will.
Well, it should add to something.
Oh yeah, they add up to something.
Let's add up to what?
Adds up
The
to 45.
total exam adds up to 135.
Yeah.
Okay, I will fix that.
Okay.
And I think your question 2 adds up to 45, but it says 35, and then 1 says 80, but it's 90.
Okay, I will change.
the response variable y is just attendance in this case.
Yeah. Yes.
So for 2A, you said use the alpha and beta matrix. Do we know what the variance refers to?
Just unweighted units.
Oh, just use unweighted? Okay.
Are there any stupid questions out there that you've been dying to ask, but were felt as though you shouldn't? Much better to get them out of the way on a Friday afternoon than suffer through the weekend with them.
I have two other comments on the exam. First, so when you submit your code, make sure, try your best to, when you import the data, use the relative file path and include the data in your folder. So when I open your code, I can have all the data imported correctly. So an example will be our answer key for exam 1. So when you open all our codes, you can have all the data imported correctly.
In the same directory as the MathCAD file.
Yeah. Okay, and the second one is just remind you the office hour will be up on Sunday at 8 p.m. So if you want to sign up it, I will change the red indicates turn to green as around 8 p.m. And make sure you don't accidentally overwrite others' names.
It can happen more easily than you think, because if two people are writing at the same time, whoever clicked enter last will win. But we do have a record of who clicked first as well, so just look out for that and double check that your name is in there a couple minutes later, just to confirm that it went through all right. Yeah.
Yes.
For the proof right there, is that written out?
Yeah, it's a pen on the paper. Yeah.
Just 2 questions. No, 2 questions on the exam.
Sort of.
Broken down into many parts. Okay. In that case, good luck. Have a good weekend, or at least try to. Yeah, take some time off on Easter. Oh, let me go ahead and stop the recording.
Yeah.
Did it not record? No, it's got to be recording.
If not necessary,
I don't see it going.
just like, for example,
Oh, here it is.